Welcome to the next lecture on basic theory of fluid mechanics. Friends, we have seen quite a lot of lectures covering the thermal part of it. Thermal and fluid overlap, as I told you in the lectures. Here we are trying to take a fluid wherein which it is incompressible. So that's what we are trying. So that's why fluid mechanics also plays an important role in real-time usage. In this lecture, we will try to cover with a small introduction. Then we have Lagrangian concept, Euler concept. We will move from Lagrangian and Euler to control volume, control surface. Then we will try to look at some of the laws wherein which we try to look at hydrostatic laws, Pascal's law, and then Bernoulli's theorem. These are the fundamental principles for a lot of real-time applications. For example, if you want to have a lift, hydraulic lift, which is used in forklifts, you want to elevate the height, bring down the height. You want to use it in machines where the piston moves up and down. So everywhere we use these three principles, one or all the three, to get to an application. So for technology, these three laws are very important. Fluid motion can be generally described in different ways, particularly at the macroscopic level. Macroscopy means larger level, which deals with fluid as a continuum media. There are two approaches used for this analysis. One is Lagrangian concept, the other one is Eulerian concept. In Lagrangian concept, we focus on following the motion of individual particles over time. For example, if there is a fluid flowing through a pipe, and we wanted to analyze what is going on, what we do is we try to take individual particles and try to note down with respect to time what happens to this particle. For example, if you take an agarbatti and you have an agarbatti which is there, this has a aromatic smell which gets dispersed all through. You can see, assuming that there are particles mixed in it, you can try to see the particles, what is happening to the movement of the particles over a period of time. By doing so, you can try to figure out after a certain period of time, where do these particles get trapped or get dispersed in air. Okay? So that is done by the Lagrangian concept. The other one, Eulerian concept, is nothing but the focus on observing the fluid property as they pass through a fixed point in space. So you stand like a policeman and you try to see what is happening at that point of time around, is what Eulerian concept. Passing through fixed points in space or a fixed region is Eulerian concept. So a typical schematic comparison between Eulerian framework and Euclidean framework. In Eulerian framework, you can see these are four particles which are trying to move along with the fluid. Many a times we try to disperse fluorescent light, or we try to functionalize something, and when you pass a fluid, we try to see how does the particle moves. Or when we try to use an equipment called particle PIV, velocimetry is measured, right. So there what we do is we try to look at the particles over a period of time, how does it work. So here we are trying to use particles, we are trying to record how the particle move over a period of time. So you can see here this tube assuming that it is flexible. When the pressures increase, you can see here with t equal to 1 second, this is trying to get dispersed or it is trying to get bent. So then you can see here at t equal to 1 second, t equal to 2 second and t equal to 3 second. So you can see the distances, how the distance has changed with respect to time. But whereas when you come to Eulerian framework, you have kept the thermocouple or you have kept the end point of the pressure gauge, which tries to measure the fluid flow. Now, as and when the flexible tube gets bent, you see here it comes to the extreme end. Maybe at some point of time it misses to even record any value here. But all you are doing is with respect to that fixed location, we try to see what is the response. Generally, wherever we try to put a pressure gauge, thermocouple or for a temperature measurement or for velocity measure, so the sensor will be fixed at a given point. From there, we try to use this Eulerian viewpoint. The concept of control volume and control surface comes into existence. Control volume, it is a finite fixed region in space chosen for analysis in Eulerian framework. So, you are trying to take all the green portion here. You cut a frame or a plane and then you try to take inside the plane or inside that particular frame what all is there. So, that is called as control volume. It remains unchanged in position and magnitude over period of time. So, this control volume is fixed with respect to position and magnitude over time. When we try to look at control surface, the control surface is the bounding surface of the control volume. So, in the control volume, you have an area. So, if you give a thickness, it becomes volume. So, if you can encapsule the volume, then that becomes a surface. If it is done in 3D, it becomes surface. If you do it in 2D, it becomes a line. Right? So, control surface, this is the bounding surface of the control volume. The fluid particles pass through the control surface, means the same fluid particles are not contained within the control volume at different times. When we use this Lagrangian concept or description of fluid motion is a method where you follow an individual particle as they move through a space or a time. Some of the key aspects of Lagrangian concept are it involves tracking specific tagged or identified fluid particles as they move through the flow field. Flow field is the fluid is flowing. The fluid properties such as temperature, velocity, density are determined by observing these individual particles. In the Lagrangian viewpoint, a fluid property associated with a specific particle is considered a function of time as the particle position changes. Even when you try to do a compression test, you put the particle in one place and when you start pressing, it moves up or down. When you start stretching, it moves up or down. Right? So, that is what we are trying to say. In the Lagrangian viewpoint, a fluid property associated with a specific particle is considered a function of time as the particle's position changes from location to location. For example, when you go back and look at t equal to 1 second, you see where have the yellow dots gone. When it is 2 seconds, you see where has it gone, and 3 seconds, where has it gone. So, for instance, the temperature of a particle A might be described as T equal to T, which is a function of x naught, y naught, z naught with respect to time, whereas x naught, y naught, z naught are the initial position at a time called as t naught, at the initial position. As and when it moves, then it becomes x1, y1, z1, t1. If it is n, it becomes t at xn, yn, zn with and at a time tn, we can try to find out the temperature. A primary visualization tool for the Lagrangian description is the path lines. So, this is why path lines are very important. Path line is defined as a trajectory or a path traced out by a single fluid particle as it travels over a period of time. So, you see here, this is a particle which is traveling with respect to time. So, a path line is defined as a trajectory. Trajectory means a path or path traced out by a single fluid particle at various time intervals. So, you see here, when t equal to 0, where was it? How did it move from here to here over a period of time? And you try to draw the trajectory or the tangent for every point, and that one is called as the streak lines. Streak lines through the origin at time equal to t, right? The path line of a particle at original at time equal to t is like this. So, you try to draw 0, the y-axis you will try to have v naught by u naught. Along the x direction you try to have the coordinates. So, the straight line defines t equal to pi by 2 omega. So, this axis y defines the path line of a particle at a time t equal to at a time t. And here the streak lines, these dotted lines are called as streak lines. They through the origin at a time t you try to draw. The figure illustrates this, showing the path of a particle at its position / velocity is given here. So, this is the path line, the dotted lines are path lines, and you can see here how the path line varies, and these are streak lines. So, what it moves, these are called as streak lines. So, the focus, Lagrangian description focuses on observing a specific fluid particle as it moves through a space. Instead of looking at a fluid property at fixed point in space, the Lagrangian approach traces the property of individual particles. So, a finite, so you can see here, these are the coordinates x, y and z. Converting control volume carrying the fluid element is called as Lagrangian representation. So, you can see here the converting control volume CV, this is the volume which we were discussing, and this is the surface. So, the volume is here. So, the same particles stay inside the control volume, right, as and when it is moving. So, the finite control volume Lagrangian flow model is shown here. The description, in this view, the fluid properties such as velocity, pressure, density and temperature are described as a function of time for these individual particles. For example, the temperature of a specific fluid particle, say A, at a particular time t can be defined by this way. This is distinct from Eulerian description, where the properties are given as a function of spatial location x, y, z and t, as I described earlier. So, you can see here, this is the flow, this is the location at 0, then the time is defined as this. So, here this is x, this is y. We are trying to take a 2D, so there is no z, and then you can see here the particle is moving. Temperature A can be defined as at the temperature A with respect to time. So, the observation is, in Lagrangian concept, you observe the behavior of a fluid by imaging a measuring device attached directly to the fluid particle, recording its property as it travels. For example, a temperature sensor would move with the particle and continuously record its temperature over a period of time. By tracking many such particles, you may build a complete picture how property changes along its path. So, how property changes along its path. So, this is what we are trying to talk. When the particle is moving along, so how does it change its property? The Eulerian concept is a fundamental way to describe how fluid move and how their property change. It also talks about the same, but how the property change. Think of it like standing still and watching a fluid flow past you. So, assuming that there is a river flowing and there is a fish. So, you are standing here and then watching what happens to the fish when it comes here and then which goes out of your sight. The focus is Eulerian method focuses on describing what is happening at specific fixed point in space. Earlier, it was moving along. So, it is at a fixed point. You don't follow individual bit of fluid. Instead, you pick a spot, say x, y, z, and measure things about the fluid as it passes over that particular spot over a period of time. So, this is the control volume and this is the control surface. So, the fluid is flowing through. The Eulerian representation is a controlled volume in space with fluid elements flow in and out of the control volume. So, the description in this view, the fluid property like velocity, pressure, density and temperature are described as a function of the location and time. For example, the temperature at a point x, y, z at a specific time t is given by this equation. What you observe, an observer using Eulerian method stay at a fixed location and record the property of the fluid that flow through that point. The value of these properties might change at the point over time if the fluid is unsteady, or they might be different at different fixed points at the same time. So, when the fluid is unsteady, you can see here how the fluid is flowing. So, the value of these properties might change. What are the values? The values of x, y, z with respect to t might change at that point over time if the flow is unsteady. If it's a steady flow, there is not much of change. When there is an in reality, there will be always unsteady flow, or they might be different at different fixed points at the same time. So, when we compare the concept of Lagrangian with respect to Eulerian, you move along the object or particle is Lagrangian, and Eulerian is you stay at one place. Best if you want to know the journey of the same point of about something with respect to time, you can try to get in Lagrangian. Best if you want to know what happens at a given location. The changes are seen as the object is moving. The changes are seen as things pass through the point. Like following a single car on a road is Lagrangian. Like standing at a bus stand watching the car passing is Eulerian. So, this is what happens in reality. Eulerian, you can see here, I told you, this is like standing at a bus stop watching cars passing by. There are a lot of fluid which is flowing. These are fields. So, you can trying to record it and then try to see what is the velocity vector. So, when you try to talk about Lagrangian, it is with respect to a particular particle, how does it change its position or whatever it is. So, x, y is changed into x dash, y dash. The control volume is a fundamental concept used in Eulerian approach, and this is very commonly used. A control volume is defined as a volume in space, a geometric entity independent of mass. Please note that it is a geometric entity which is independent of mass. The purpose is, instead of following an identified amount of fluid mass which is focused on Lagrangian system approach, the control volume method involves analyzing flow and fluid property through the defined or stationary volume. So, you can have a ring through which it passes. Every time I note the ring. So that's what passing through a defined stationary volume. It's often used because it can be difficult to track individual fluid particles or a specific mass as they move and deform. So when you start to notice a particle moving, coming out of the agarbatti stick, you can try to trace it for some time. But if it gets diffused, you will not be able to track. So when the fighter plane moves in the sky, you can see once it exits, it leaves back a straight line. And over a period of time, this gas which exits out gets diffused slowly in the atmosphere. So till that time it is getting diffused, you can track its path. Moment it diffuses, you cannot. So that's what it is often used, because it can be difficult to track individual fluid particles or specific mass as they move and deform. Okay. So this is what we are trying to see. The focus of control volume is the analysis concentrates on what happens within the control volume, what it is entering and leaving the control across its boundary, which are collectively called a control surface. So this boundary is the surface. The analysis concentrates on what happens within the control volume and what enters or leaves the volume across its boundary. Why is it important? Because the boundary conditions can give heat, can remove heat. So across its boundaries, which are collectively called as control surface, the property like mass, momentum, energy within the control volume can change over a period of time. Note this point. The mass, momentum and the energy within the control volume can change over a period of time. What is now T equal to 0, when T equal to 5, the diffusion can happen, there can be resistance, there can be energy change. The application of this law, fundamental conservation law such as conservation of mass, conservation of linear momentum and conservation of energy are often applied to control volume to solve practical fluid mechanics problem. So when there is a fluid problem to be solved, we always look at conservation of mass, conservation of linear momentum and conservation of energy. These are the three things we try to solve to understand what happens to the fluid motion with respect to time. So these are the application of laws. So friends, keep that in mind. The law of conservation of mass, of momentum and of energy is important. And when we talk about new momentum, it is second law of Newton, which we studied, comes into existence. Okay. And the first one, conservation of mass, is nothing but this is continuity. Continuum equations have to be done. So fixed control volume, the types of control volume are fixed control volume, moving control volume and deforming control volume. There are three. So control volume, there are three types: fixed, moving and deforming. These are the three possibilities. Suppose I have a cylinder. The cylinder is located at one point. The cylinder is moving with respect to time. The third one is cylinder gets deformed with respect to time. Three conditions possible. Fixed control volume for all the three. It is a region in space that remains stationary. Always it is stationary. The analysis using a fixed control volume focuses on what happens to the fluid property as they flow in, through and out of this fixed region. So this is in, out, through the fixed region. The figure shows a fixed control volume across a section of a pipe. So, you can have the velocity coming V and then the velocity exiting V dash. So, at the entry point, at the exit point. So, this is fixed control volume. This volume has to be confined through a pipe. So, that is why we have a pipe here. So, this is a fixed control volume. Next one is moving control volume. Is the cylinder whatever is there, you are moving it. You are moving the cylinder. This was a cylinder at a fixed point. So, when you are trying to move a control volume, this type of control volume moves through space, typically translating a certain velocity. So, this one translates at a velocity of maybe 5 meters per second. Its shape may or may not change. When it is moving at this velocity, it might or might not change. The figure shows a fixed or a moving control volume around the jet engine intake. So, this is intake and this is exit. So, this is a moving control volume. The next one is deforming control volume. This control volume boundaries changes the shape or size over time. So, you have a balloon, you blow air into the balloon over a period of time, and suppose you tie it, then it becomes a fixed volume or a control volume. Once you remove the knot, the air escapes out. Now, the shape gets deformed or the size gets deformed over time. A deforming control volume can also be a moving volume. Why? Because the balloon will move at multiple directions because there is a air which is going out. So, that will give you a thrust, this will keep moving. So, this figure shows the deforming control volume around a balloon, right. So, these are 3 different types. All these things play a very important role. When we are trying to talk about a cricket match, a swing coming, or when we are trying to talk about a football kick, a rainbow kick, all these things when they talk about is showing the moving control volume around the ball. So, a control surface is a boundary of a control volume. It is a key concept in the Eulerian method for describing fluid flow. The purpose of this control surface is to define the region around the fluid property are absorbed. So, you are saying here is a fluid which is done, but now you are trying to put a surface so that you can confine them and then talk. So, the primary purpose of control surface is to define the region around which the fluid property are absorbed. So, this allows the analysis of mass, momentum, energy and other quantities when it flows in and out of the system. It serves as a conceptual boundary for applying the conservation laws like conservation of mass, momentum, energy for a fluid flow system in the Eulerian framework. So, a control surface is m dot mass flow, a mass flow rate is there, the mass is flowing. This is a control surface, as this is a control volume and there is a control surface. The inflow, this is when fluid enters the control volume by passing through a control surface from the outside. For example, water entering a pipe from a reservoir is a control surface. So, here if you see the control surface, the inflow portion of a control surface can be defined as CS in. So, then there is a small increment of delta A. So, it moves at a velocity V and normal to that is n dot. So, the angle traced is nothing but theta. So, the outflow, here we saw the inflow, here when we see the outflow, when fluid leaves the control volume, this is the inside whatever is there is a control volume, the closing surface is the control surface, leaves the control volume by passing through a control surface. The water exiting a pipe into a tank is called as an example for control surface. So, you can define this in terms of dl, increase in length, which is nothing but velocity into delta t. So, it moves from this point to this point. So with an additional of the delta A moves with an increase in length of delta n. N is the normal. So it can be resolved like this. So when it goes out across the typical portion of a control surface, so this is for inflow, this is for outflow. So now let us see some of the basic laws. Hydrostatic law. The hydrostatic law is a fundamental principle in fluid statics, which is a study of a fluid at rest. So hydrostatic law, static is at rest. It specifically describes how pressure varies within a fluid that is stationary. So you have a beaker you have made several holes and then fill the beaker with water. So here, as and when the water goes down, when you move down, the pressure increases with respect to depth, right? So you will have at the topmost portion, you will have the weakest jet, and the strongest jet will happen at the bottommost. So you can see here, it will go for a short distance. This fellow will go for a longer distance. So it specifically describes how pressure varies in the fluid when it is stationary. When the hydrostatic law, what hydrostatic law states? It talks about absence of shear stress. The foundation of fluid statics and the hydrostatic law is that a fluid at rest cannot support shear stress. This means that the normal stress on any plane through a fluid element at rest is a point property called fluid pressure. So there is absence of shear stress is the important point. This pressure itself is a thermodynamic property, not a force. And there is no direction. The forces arise when pressure acts on the surface. The pressure gradient in the vertical direction, this is delta H, the pressure whatever comes is delta P. The pressure gradient in vertical direction, the core mathematical statement of the hydrostatic law is that the pressure gradient in the vertical direction is directly dependent on the specific weight of the fluid. So it is given by this equation. In the coordinate system, where Z is the vertical and positive is upward, this can be expressed as dP by dZ. Pressure drop over the Z direction is minus gamma. So that is where P is the pressure, Z is the vertical coordinate, gamma represents the specific weight of the fluid, which is nothing but weight per unit volume. The negative sign is crucial because it specifies that the pressure decreases as one moves upward in the fluid and increases one move downward in the fluid. So this negative is very important. This aligns with our everyday experience, such as the pressure increases as you dive deeper into the water. When you try to take a cup deep into the water, there is lot of pressure, which is uniform pressure exerted over the cup crumbles and becomes small. When you dive deeper into the water, yes. So the pressure increases as you dive deeper into the water. So the hydrostatic law you can see here, which is represented the pressure on a tank bottom, P equal to 0, the pressure on a tank end, which is in the top, the specific weight is gamma. So H is the height. So here the force whatever is getting applied is P equal to gamma H. So as and when at the top whatever comes, at the tank bottom it is like this. At the tank end, which is on the other side, where you will see that the pressure P is nothing but gamma H, which is acting this way towards the walls. The pressure distribution and the resultant hydrostatic force on the bottom of an open tank is given in A, and the pressure distribution on the tank on the end of an open tank is given by B. So this is at the end of the tank is given. So this is at the bottom, this is at the side end. So, incompressible and linear variation, the fluids are incompressible, or if for an incompressible fluid where the density and thus the specific weight are essentially a constant, the hydrostatic law integrates to a simple linear relationship. Delta P is equal to minus gamma times delta Z. So, it follows a linear model because the fluid is incompressible. So, alternatively, if P naught is the pressure at a free surface, atmospheric surface, H is the virtual height below that surface, the pressure at a depth given is defined by this equation, P equal to gamma H plus P naught. This means that the pressure increases linearly with respect to depth. This can be used, and there are multiple sensors which are getting developed today. To measure the pressure, we use a device called as manometer. The most direct and common application of hydrostatic law is in device designed to measure pressure and pressure difference known as a manometer. There are piezometer tubes used to use the height of a single fluid column to determine the pressure at any given point. So, we can use the pressure sensor. Piezometric tubes are also used, and you can use manometers to measure. The pressure measurement through a manometer, you have used this in your school days. We use a U-tube manometer which utilizes the difference in the fluid column. The difference in the fluid column is H, height, to measure the pressure difference between 2 points or between a point and the atmosphere. 2 points, or one which is atmospheric pressure and the other one is the pressure what really happens inside a system. So, you can try to measure it by using a U-tube manometer. The inclined tube manometer also can be used. Compared to the vertical one, the inclined one is more sensitive by tilting the manometer tube. More advanced pressure measuring devices like the Bourbon tube and the pressure transducer also rely on the pressure traceable to hydrostatic pressures. Next one is the Pascal's law. First we saw the hydrostatic law. Next one we are seeing the Pascal's law. Law states that a pressure at a point in a fluid at rest is independent of direction as long as there is no shear stress. This is what Pascal said. So, the pressure at a point in a fluid at rest is independent of direction as long as there is no shear stress. This means that if you have a fluid at rest, the pressure exerted by the fluid at any given point of time will be same in all directions, let it be vertical, horizontal, or at an angle. This condition of zero shear stress is a defining characteristic of a fluid at rest, and this is crucial for the deviation of both Pascal's law and bordered hydrostatic law. Pascal's law, you can try to have several applications. Original force F1 which is applied P1 into A1. A1 is smaller here, A2 is larger here. So, the pressure is nothing but force per unit area. So, here the pressure is nothing but force per unit area. So, the pressure exerted here is large. The pressure what comes here is smaller. So, the output is F2 is equal to P2 into A2. It is 10 times into greater than the original force. Right? So, P2 is equal to F2 by A2. So, this is how you try to calculate. So, whatever is the fluid used here is under static condition. So, there is no shear stress. So, the mathematical expression for Pascal's will be when applied to a fluid at rest, that can be Px equal to Py equal to Pz, where Px is the pressure acting on a tiny surface oriented perpendicular to the x-axis, and Py is perpendicular to the y-axis. Pz is perpendicular to an arbitrary inclined s-axis at the same point within the fluid. So, some of the applications of Pascal's law is hydraulic lift, used to lift heavy objects like vehicles in garages and in workshops. The pressure applied to a small piston, so you pump it, is transmitted through a hydraulic fluid to lift a very large piston. So, this is a large piston. Applying the force and allowing heavy loads to be raised with minimal effort. So, wherever we use hydraulic for lifting, locking, holding, we use Pascal's law. So, this is the hydraulic jack which is commonly used in automobile repair. This device uses Pascal's law to multiply the force by a confined fluid in two connected cylinders, 1 and 2, over a different cross-section area. The cross-section area changes. When you press the small portion of a hydraulic jack, the pressure you create is transmitted equally throughout the fluid, allowing a small input force to lift a very heavy load. So, this is Pascal's law in action. So, it can be used in elevators, it can be used in aircraft controllers. See, today we use the hydraulic drives in your power steering, in your trucks, is all based on Pascal's law. So, blood pressure measuring device also works on Pascal's law. The medical device like blood pressure cuffs work on Pascal's law by transmitting and measuring pressure uniformly within the cuff to gauge the artery pressure. Finally, we will try to look at Bernoulli's theorem or Bernoulli's equation. So, Bernoulli's equation is also known as Bernoulli's theorem, is the fundamental equation in fluid mechanics. In essence, this describes a relationship between pressure, velocity and elevation of a moving fluid. Pressure, velocity and height. Specifically, Bernoulli's theorem states that for a steady, inviscid, which is a frictionless and incompressible fluid flow, the sum of the pressure, the kinetic energy per unit volume and the potential energy per unit volume remains constant along a streamline. We saw what are streamlines. So, Bernoulli's theorem is used to explain why does an aeroplane lift. So, you have a wing which follows an aerofoil design. So, aerofoil which follows aerodynamic principles. So, here the pressure at the bottom is slower, the pressure moves on the top is faster. So, there is a lift phenomena which is given. That is why the plane takes off. The pressure by slower moving air is in the bottom of the wing. So, the mathematical formulation of Bernoulli's theorem will be expressed by this way: P plus half times rho v square plus gamma z is equal to a constant, where P is the static pressure at any given point of time, rho is the density, v is the velocity, gamma is the specific weight which is there, z is the height in the z direction. So, the rho is the static pressure of a fluid at a given point. It is the pressure that the fluid exerts when it is not moving stationary, or the pressure measured by a device moving in the fluid. So, I said at a constant point. Half rho v square is the kinetic energy per unit volume. Rho is the density and v is the velocity. If you look at gamma z is the potential energy per unit volume of a fluid due to the its elevation. Gamma is the specific weight of the fluid, which is its weight per unit volume. Z is the elevation of the fluid relative to a chosen reference point is Z, height. This term accounts for the energy due to height. So, you can see here P1 alpha 1, here it has a larger, the area is large A, the area is small at B. So, the velocity will increase. So, P2 at alpha 2 or A2, right. This is H1, this is H2. So, what is a delta H is H1, delta H is nothing but H1 minus H2 or H2 minus H1. So, the applications are aeroplane wings, the Lift generation is by the Bernoulli's principle. The unique shape aerofoil of a plane wing causes the air to move faster over the top than underneath, which creates a lift. This creates a lower pressure above the wing and a higher pressure below the wing. Lift is given to the plane such that it goes up. The sailing and a curved ball sports. The sailboat uses a principle of harnessing wind more effectively, and the curved flight of balls in sports like baseball and cricket is explained by difference in the air velocity and pressure on either side of the wall, which is called as Magnus effect. So in football, in 1997, the Brazilians won the game. It's by the goal which is created when there was a goal post, the ball was kicked and the ball moved in air like this. This happened because of difference in pressure. So that is what we are trying to talk about. Both sports like baseball, cricket is explained in the difference in the air velocity and pressure which is created around the ball. The Bunsen burner and the carburetor also works with Bernoulli's theorem. The carburetor, a fast moving stream of air, creates a low pressure area drawing a fuel into the airstream. So what happens is you will have air which is coming and then you have a fluid which is flowing. Now somehow the fluid has to be sucked inside the air. So there we use the Bernoulli's theorem. The carburetor, a fast moving stream of air, creates a low pressure, fast moving creates a low pressure area. Because it is a low pressure area, the fluid gets sucked inside the stream. Similarly, in Bunsen burner, the low pressure creates a fast moving gas pull in air for combustion. The pitot tube, which is used in aircraft to measure the pressure. The aircraft of some industrial application use pitot tubes, which measures the fluid speed by comparing the pressure at different points directly relying on Bernoulli's theorem. So they measure at different points and then they try to tell you what is the pressure there. The Venturi meter, which is nothing but a convergent divergent nozzle we use. So here there is a diameter D1, the direction of air is flowing. There is a convergence which happens. Then there is a diameter which is measured D2 at the throat, and then there is an expansion which is caused in the divergent nozzle. So D1 is the diameter, D1 is the same diameter on the other side, D2 is the throttle one. At three places you can try to measure the pressure. So this is called as a convergent divergent nozzle. This is used to measure a flow rate of a liquid in pipes. Suppose you want to do this, you create also bubbles. So these bubbles are used for cavitation and for cleaning. As the pipe narrows, the fluid velocity increases and the pressure decreases, which allows flow speed to be calculated at different pressures. So if you want to calculate a pressure here and here, it is possible by using the Venturi meter. Friends, to recap, what all did we see in this particular lecture? We saw the basics of fluid mechanics. Then we saw Lagrangian concept, wherein which particle velocity is measured with respect to time. And then we saw what is Eulerian concept. Eulerian equation concept is at a fixed space you stand and note down the fluid flow. So then the difference between Lagrangian and Euler was seen. Then from there we moved to control volume. The volume is covered by a space. Then we understood what is control space. While going through control volume, we saw the need for it and what are the various types, which was fixed, moving and deforming. Then we went into control surface. Then the purpose of control surface also we saw. So there we saw a normal vector coming into action. So since it's a basic course, we are not getting deeper into these concepts. Then we moved into hydrostatic. Then we saw application of hydrostatic. Then Pascal's, then use of Pascal. Finally, we saw Bernoulli and use of Bernoulli's theorem or Bernoulli's equation. So at the applications, we saw how does the fluid help in converting into an action. So that's what we saw in hydrostatic. In hydrostatic, Pascal and in Bernoulli's, we assume that there is no shear stress. So, this is what we saw in this particular lecture. I am sure next time when you see some of the applications, you will be able to map yourself to hydrostatic law, Pascal's law and Bernoulli's theorem. These are the references we have used in preparing this lecture. You can use this and try to have more understanding. However, the TA will be helping you while solving the problems. Thank you very much.